What if I told you the moon's far side is fundamentally different from what we see every night? Like uncovering a secret side of a familiar face, China's Chang'e E6 mission just returned with the first ever samples from the lunar far side, revolutionizing our understanding of Earth's only natural satellite. Initial analysis reveals striking differences between the two lunar faces, a discovery that could explain why they evolved so differently over billions of years. The far side contains significantly less water than the near side, pointing to a mysterious lunar history we're only beginning to unravel. These findings represent a critical turning point in lunar science in our quest to understand cosmic evolution. The lunar divide, two faces of the moon. The moon isn't the uniform sphere many assume it to be. In reality, our celestial neighbor has two dramatically different faces that evolved separately over billions of years. This asymmetry has puzzled scientists since we first glimpsed the far side in 1959, when the Soviet Luna 3 spacecraft captured the first images of this hidden lunar landscape. When you look up at the moon from Earth, you're always seeing the same face, what astronomers call the near side, with its distinctive dark patches visible to the naked eye. These areas, called Maria, Latin for seas, formed when ancient volcanic eruptions flooded large impact basins with dark basaltic lava between 3 and 3.5 billion years ago. The near side's geography features these Maria covering about 31% of its surface, including the Sea of Tranquility, Apollo 11's landing site, the Sea of Serenity, and the Ocean of Storms. The far side, however, appears to belong to an entirely different world, like two halves of an ancient coin with entirely different engravings. The dark Maria that characterize the near side are virtually absent, covering less than 1% of the surface. Instead, the landscape is dominated by craters upon craters, a rugged, heavily pockmarked terrain that bears little resemblance to the moon familiar from Earth. Why would two sides of the same celestial body develop so differently? The moon's tidal locking explains why we always see the same face, but not why the hemispheres evolved along such different geological paths. Scientists have proposed various explanations. Perhaps the moon's crust is thicker on the far side, impeding magma flow. Maybe Earth's gravitational influence affected volcanic activity, or possibly a large impact distributed heat producing elements unevenly, causing more volcanic activity on the near side. These remained theories because since Lunar's first grainy images, we lacked the most essential evidence, actual rock samples from the far side. While the near side has been extensively sampled, with over 380 kilograms of material returned by Apollo and Luna missions between 1969 and 1976, no mission had ever brought back a single gram from the far side. The South Pole-aitken Basin on the far side represents a geological treasure trove. This immense impact crater spans 2,500 kilometers in diameter and reaches depths of 8.2 kilometers, making it one of the largest known impact structures in our solar system. Formed approximately 4.3 billion years ago, its tremendous depth likely penetrated deep into the moon's crust, possibly excavating material from the lunar mantle and creating a window into the moon's interior composition. The basin contains evidence of volcanic activity different from near-side Maria, with deposits showing distinct chemical signatures. It preserves records from the late heavy bombardment period, approximately 4.1 to 3.8 billion years ago, when the inner solar system experienced intense asteroid impacts. The region may also contain clues about the moon's magnetic history. As studies suggest, the moon once had a global magnetic field that disappeared around 3.2 billion years ago. Given these potential discoveries, the South Pole-aitken Basin became a priority target for China's lunar exploration program. The Chang'e 4 mission made history in 2019 by achieving the first ever soft landing on the far side within the Von Karman crater inside the basin. While this mission analyzed surface composition in situ, it couldn't return samples to Earth for detailed analysis. Chang'e 6 transformed lunar science by successfully landing in the Apollo basin on the far side on June 1st, 2023, and returning approximately 2 kilograms of lunar material. These precious samples provided scientists with the first ever physical materials from this mysterious hemisphere, allowing precise analysis of mineral composition, water content, isotopic ratios, and age. Initial findings have already begun reshaping our understanding of lunar asymmetry. The samples contain evidence that volcanic activity on the far side continued for at least 1.4 billion years, longer than previously thought. They also reveal significantly less water than comparable near-side samples. Most importantly, they offer direct evidence explaining the moon's asymmetrical development. Compositional differences between near-side and far-side materials point to fundamental variations in formation conditions and evolution. The success of Chang'e 6 highlights how limited our previous lunar exploration had been. Despite Apollo's monumental achievements, half the moon remained completely unexplored by sample return missions until now. The technological challenges of operating on the far side, particularly the communication barrier created by the moon blocking direct radio signals to Earth, prevented earlier missions from accessing this territory. The Chang'e 6 samples connect directly back to those first Luna 3 images that revealed the moon's hidden face. What began as grainy photographs showing an unexpectedly different lunar hemisphere has evolved into physical samples we can analyze in Earth laboratories, bridging a 64-year gap in our exploration efforts. As we examine these groundbreaking samples, we're gaining insights into fundamental processes that shaped the entire inner solar system. The lunar far side preserves a record of the early solar system relatively untouched by volcanic resurfacing. By comparing both hemispheres, scientists can construct a more complete picture of our solar system's formation. With these new samples in hand, we enter a new era of lunar science. But collecting them required overcoming tremendous technological hurdles that previous missions couldn't surmount. Let's look back at how lunar exploration began and the limitations that kept us restricted to the moon's near side for so long. Apollo's legacy, the first giant leap. July 20th, 1969. The world watched as Neil Armstrong took those first historic steps onto the lunar surface, declaring it one giant leap for mankind. This moment marked the pinnacle of human space exploration, the culmination of a decade-long race that pushed technology to its limits and expanded our understanding of both Earth and its celestial neighbor. Over the next 3 years, 5 more Apollo missions would land on the moon, with 12 astronauts exploring the lunar landscape and returning with a scientific treasure trove of moon rocks and soil samples. Yet for all their remarkable achievements, the Apollo missions had significant limitations. These pioneering expeditions explored only a tiny fraction of the moon's surface, all on the familiar near side that faces Earth. The far side remained completely untouched by human hands or sample return missions, a situation that would persist for over 5 decades until Chang'e 6's breakthrough. The Apollo program represented an extraordinary technological achievement for its time. The missions utilized advanced rockets, spacecraft, and computers available in the 1960s and early 1970s. However, these technologies were primitive by today's standards, with computational limitations that restricted the spacecraft's autonomous capabilities and required constant human monitoring and control. More importantly, the Apollo missions operated under a fundamental constraint: the need for continuous direct communication with Earth. The spacecraft and lunar modules were designed around a direct line-of-sight radio link between the astronauts and mission control in Houston. This communication architecture worked perfectly for near-side operations, where radio signals could travel unimpeded between Earth and the Moon. However, it made far-side exploration effectively impossible. The Moon itself blocks all direct radio signals from the far side to Earth. Without relay satellites positioned in lunar orbit or at Lagrange points, astronauts landing on the far side would be completely cut off from communication with mission control during the most critical phases of their mission. In the event of an emergency, they would have no way to call for assistance or receive guidance. Given the already considerable risks involved in lunar landings, NASA deemed this communication blackout an unacceptable safety hazard. The Apollo program lacked the satellite infrastructure necessary to enable far-side communications. While technically possible to deploy communication satellites in lunar orbit, this would have required additional launches and spacecraft development at a time when the program was already pushing the boundaries of available technology and budget. Sample collection methods employed during Apollo missions were remarkably straightforward. Astronauts used basic hand tools including hammers, tongs, scoops, rakes, and core tubes to collect lunar material. They would visually identify interesting rocks, sometimes based on radio guidance from geologists on Earth, then physically pick them up and place them in sample bags. This approach was limited by what the astronauts could see and reach during their relatively short surface operations. Apollo core samples reached only 3 meters below the lunar surface at their deepest. While valuable, these samples only scratched the surface of the moon's geological history. Deeper material, potentially containing evidence of the moon's early formation period, remained inaccessible with the tools and time constraints facing Apollo astronauts. The geographical diversity of Apollo samples was similarly constrained. All 6 landing sites were situated on the near side, between 26 degrees north and 9 degrees south latitude, mostly in equatorial regions. These sites were selected primarily for safety considerations rather than maximum scientific return. Though later missions ventured into more challenging terrain with greater scientific interest, the entire far side and polar regions remained unexplored. Mission planning for Apollo required extensive human involvement at every stage. Landing sites were selected years in advance based on photographic surveys from lunar orbiters. The missions followed meticulously planned timelines with limited flexibility to adapt to discoveries or changing conditions. This rigid structure was necessary given the communication and computational limitations of the era, but restricted the mission's ability to respond to unexpected findings. Between 1969 and 1972, the 6 landed missions collected 382 kilograms of lunar material comprising more than 2,200 separate samples. Analysis of these samples revolutionized our understanding of the moon's composition, age, and formation history. They provided evidence that the moon formed approximately 4.5 billion years ago, likely resulting from a massive collision between Earth and a Mars-sized planetary body. Dating of the samples showed that major volcanic activity on the lunar near side occurred between 3.1 and 3.8 billion years ago, creating the dark Maria visible from Earth. The scientific value of these samples continues today. Scientists analyze Apollo samples using increasingly sophisticated techniques not available when they were first collected. Each new generation of analytical instruments reveals new insights from these 5-decade-old samples. However, all this knowledge came exclusively from the moon's near side, leaving half the lunar surface unexplored. Apollo missions never ventured to the South Pole-aitken Basin or any other far-side location. This one-sided view of lunar geology left major questions unanswered about the moon's asymmetrical development and overall geological history. The same communication limitations constrained subsequent missions. The Soviet Luna missions, which returned small automated samples between 1970 and 1976, also limited their operations to near-side sites. After Luna 24 in 1976, no mission would return lunar material to Earth for 44 years until China's Chang'e 5 mission in 2020, also from a near-side location. Decades of technological advancement were needed to overcome these challenges. The development of powerful computers, autonomous navigation systems, artificial intelligence, and advanced communication networks eventually created the possibility of operating complex missions beyond direct Earth contact. These technologies, combined with China's systematic approach to lunar exploration, finally enabled humanity to access the moon's hidden face and return samples for analysis on Earth. The limitations of Apollo faced word failures of imagination, but practical constraints of 1960s technology. Now, over 5 decades later, new technology has finally overcome these limitations, unlocking the secrets of the lunar far side that remained beyond Apollo's reach. The Far Side Challenge, breaking new ground. For decades, the lunar far side has been tantalizingly out of reach for sample return missions. Unlike the familiar near side, which always faces Earth, the far side has remained largely unexplored for one fundamental reason. It's impossible to maintain direct radio communication with spacecraft operating there. The moon itself, a 3,474 kilometer diameter rocky sphere, blocks all direct signals between Earth and the far side surface. This communication barrier presented a seemingly insurmountable obstacle to exploration efforts. The moon acts as a natural fortress, with its far side holding geological secrets behind an impenetrable radio shield. A lunar sample return mission requires constant monitoring and control during critical phases like landing, sample collection, and descent. Engineers need to track the spacecraft's position, monitor system health, and transmit commands to adjust operations when necessary. Without this communication link, a spacecraft would be effectively flying blind during the most dangerous parts of its mission, even with automated systems. Sample return missions involve multiple precise maneuvers, landing safely, collecting and securing samples, launching back into lunar orbit, rendezvousing with an orbiting module, transferring the samples, and returning to Earth. Each step presents opportunities for failure, and even minor errors can cascade into mission-ending problems. For missions representing years of development and hundreds of millions of dollars, this communication void created unacceptable risk levels. China's solution to this decades-old problem arrived in the form of Keiqiao-2, meaning Magpie Bridge 2 in Chinese mythology. This 1.2-ton communications satellite launched in March 2023 specifically to support the Chang'e 6 mission. Its predecessors supported the Chang'e 4 mission in 2019, which achieved the first ever soft landing on the lunar far side, but didn't return samples. Keiqiao-2 operates from a remarkable location known as the Earth-Moon Lagrange Point 2, or EML2. Lagrange points are special positions where the gravitational forces of two large bodies and the centrifugal force of their rotation create equilibrium points. EML2 sits approximately 65,000 kilometers beyond the moon, directly opposite from Earth. From this position, Keiqiao-2 maintains simultaneous line of sight with both Earth ground stations and the lunar far side. The satellite functions as a cosmic relay station. Chang'e 6 transmits data to Keiqiao-2, which forwards it to Earth receivers. Similarly, mission controllers send commands to Keiqiao-2, which relays them to Chang'e 6. This communication bridge solves the fundamental problem that prevented previous missions from exploring the far side. Maintaining a satellite at ML2 requires precise navigation and regular adjustments. The satellite must perform station-keeping maneuvers to maintain its position against solar radiation pressure, gravitational perturbations, and other forces that could displace it. Equipped with advanced S-band and X-band communication systems, Keiqiao-2 enables high-bandwidth data transmission for operational commands, scientific data, and images. The satellite's large deployable antennas ensure strong signal strength despite vast distances, providing essential communication capability for Chang'e 6's complex operations. Even with the relay satellite, landing presented extraordinary challenges. The South Pole-aitken Basin features some of the moon's most rugged terrain, heavily cratered with destabilizing slopes and potentially damaging boulders. Unlike the relatively flat mirror regions where Apollo missions landed, this terrain offers few large, level landing areas. Chang'e 6 navigated this uncertain terrain using onboard sensors and autonomous navigation systems. The spacecraft's descent camera captured images of the approaching surface, while radar altimeters measured precise distance. Onboard computers processed this information in real time to identify hazards and adjust the landing trajectory. The landing sequence required incredible precision. After entering lunar orbit, Chang'e 6 separated its lander from the orbiter. The lander performed a powered descent, adjusting its trajectory to avoid obstacles. In the final approach, the main engine throttled down as landing legs deployed. The spacecraft needed to touch down gently enough to avoid damage, but firmly enough to prevent tipping on the uneven surface. This landing sequence occurred with minimal Earth input due to communication delays. Signals take over 3 seconds for the 500,000 plus kilometer round trip between Earth, K'Yao-2, and Chang'e 6, an eternity during landing. Chang'e 6 relied heavily on autonomous systems programmed to make critical decisions without waiting for Earth-based controllers. Sample collection also required sophisticated automation. The lander analyzed surrounding terrain, selected suitable sampling locations, deployed collection mechanisms, and secured samples with limited human supervision. Operations robust enough to succeed even during communication interruptions. The lunar far side presents extreme temperature challenges. Without an atmosphere, surface temperatures reach 127 degrees Celsius during the 2-week lunar day and plummet to minus 173 degrees Celsius during the equally long lunar night. Chang'e 6 includes multi-layer insulation, radiators, radioisotope heater units, and materials with matched thermal expansion coefficient to maintain functioning systems across this dramatic temperature range. The successful mission represents a monumental achievement that effectively doubles the accessible lunar surface for future exploration. By solving the communication barrier that kept previous missions confined to the near side, China has opened an entirely new frontier. Future missions can now target any location on the moon, including scientifically valuable regions on the far side. Scientists can now study the entire moon, not just the Earth-facing hemisphere. The far side preserves a record of the early solar system, relatively unchanged by the volcanic activity that resurfaced much of the near side. It likely contains materials and geological features providing new insights into lunar formation and evolution, enhancing our understanding of the entire solar system's early history. With the communication barrier overcome, attention now turns to the advanced technology that enabled Chang'e 6 to successfully collect samples once on the surface. Chief among these innovations was the first AI-powered lunar rover, which revolutionized how we explore other worlds. AI on the moon, the revolutionary Jinchan rover. When Chang'e 6 touched down on the lunar far side, it didn't arrive alone. The mission deployed a remarkable new explorer that represents a fundamental shift in how we investigate other worlds. The Jinchan rover, whose name translates to golden cicada, weighs just 5 kilograms, 11 pounds, but carries technology that previous lunar missions could only dream of. A sophisticated artificial intelligence system designed to operate independently in one of the most challenging environments in our solar system. This miniature rover marks a radical departure from traditional lunar exploration vehicles. Imagine a tiny explorer that thinks for itself. While the Apollo lunar roving vehicle weighed 210 kilograms and China's previous U-22 rover weighed 140 kilograms, Jinchan's compact 5-kilogram frame represents an entirely new approach to planetary exploration. Lighter, more efficient, and critically, much smarter. Traditional rovers face a fundamental limitation. They require constant human guidance from Earth. Engineers must analyze images from the rover's cameras, identify potential routes, assess hazards, and then transmit detailed driving instructions. This process creates significant inefficiencies. On Mars, rovers typically travel just 100 meters per day because of the communication delay. For a mission operating on the lunar far side, where direct communication is impossible and even relay communication experiences delays, this traditional approach becomes particularly problematic. Think of traditional rovers as remote-controlled cars that can only move when their operator can see them and press the controls. In contrast, Jinchan operates more like a self-driving vehicle, making its own decisions and finding its own path. The standard operating procedure for previous rovers involved a cycle: drive a short distance, stop, capture images, transmit them to Earth, wait for analysis, receive new commands, and repeat. This methodology limited exploration range to what Earth-based controllers could safely guide during available communication windows. Jinshan breaks this paradigm through its onboard AI navigation system. Rather than waiting for Earth-based controllers to analyze terrain and plot routes, the rover continuously processes visual data from its cameras using sophisticated computer vision algorithms. The system identifies obstacles such as rocks, craters, and slopes, calculating their size and danger level. It then generates navigational paths that maximize safety while progressing towards scientific objectives. The rover's navigation AI was trained using thousands of simulated lunar terrain scenarios. Engineers created digital twins of the expected South pole-aitken basin environment, allowing the AI to practice navigation in virtual reality before ever reaching the moon. This training enabled the system to recognize patterns in the lunar landscape and make appropriate navigation decisions when encountering similar terrain on the actual lunar surface. Jinshan's computer vision capabilities extend beyond simple obstacle detection. The system can analyze geological features to identify scientifically valuable targets. It categorizes rocks based on shape, texture, and reflectivity, prioritizing unusual specimens that might merit closer examination. This capability means the rover actively seeks out features of potential scientific interest while navigating. Perhaps most remarkably, Jinshan can independently compose and capture photographs without human direction. The system evaluates its surroundings continuously, identifying optimal camera angles for both navigation and scientific documentation. It adjusts exposure settings based on lighting conditions and selects framing to provide maximum context for features of interest. When the rover identifies features of particular interest, it automatically captures multiple images from different angles and distances, creating detailed visual records for constructing 3D models of the terrain. The AI capabilities proved particularly crucial for operations on the lunar far side. Communication between Earth and the rover must pass through the Chang'e 2 relay satellite, introducing delays that make real-time control impractical. By operating autonomously, Jinshan could continue exploring and documenting the landing site even during periods of limited communication access. Beyond its advanced AI, Jinshan's physical design represents another leap forward in rover technology. Its lightweight construction reduces launch costs and allows for deployment from larger mission components without complex mechanisms. The rover's miniaturization relies on advanced materials and highly integrated electronics. Its frame uses carbon fiber composites that provide structural strength while minimizing weight. Power comes from efficient solar panels supplemented by advanced battery technology that maintains performance across extreme temperature variations. Jinshan's mobility system uses a specialized four-wheel arrangement with each wheel independently powered and controlled. This provides maximum traction with minimum complexity and weight. The wheels themselves are designed with flexible metal mesh surfaces that conform to irregular terrain while resisting the abrasive effects of lunar dust. During its operations, Jinshan captured unprecedented images of the far side landscape, providing essential context for understanding exactly where the Chang'e 6 samples originated. The rover documented the immediate surroundings of the lander, the specific sampling locations, and the broader geological context of the landing site. It identified several unexpected features not visible in orbital imagery, including small-scale impact structures and unusual rock formations. Jinshan demonstrated a new model for planetary exploration, one where robots make intelligent decisions on their own, rather than functioning as remote extensions of human controllers. This approach fundamentally changes what's possible in space exploration. Future missions incorporating similar AI could explore larger areas, respond to unexpected discoveries without waiting for Earth-based instructions, and operate in environments where communication delays make traditional control methods impractical. With the landing site thoroughly documented by Jinshan's cameras, Chang'e 6 could proceed to its primary objective, drilling into history, the sample collection process. Collecting samples from the lunar surface isn't simply a matter of scooping up some dust and rocks. The Chang'e 6 mission employed a meticulously engineered multi-stage process to extract, preserve, and return pristine material from a location that has remained virtually unchanged for billions of years. This complex operation had to function flawlessly despite the extreme conditions of the lunar far side. Where temperatures swing from scorching heat to frigid cold, micrometeorites constantly bombard the surface, and cosmic radiation bathes the landscape. The challenge of lunar sample collection extends far beyond the physical act of gathering material. Scientists need samples that accurately represent the geological context of the landing site, while remaining uncontaminated by Earth materials or organisms. Even microscopic contamination could compromise the scientific value of these precious materials, potentially leading to false conclusions about lunar composition or history. Chang'e 6 addressed these challenges through a sophisticated sampling system operating in two distinct phases. First, a robotic arm collected surface material with precision that far exceeded the shoveling techniques used by Apollo astronauts decades earlier. The 2.1-meter arm extended from the lander's main body, positioning itself above predetermined sampling locations selected based on Jensen rover imagery and orbital data. At the arm's end, a specialized scoop mechanism with titanium alloy blades cut into the lunar regolith. The system applied calculated pressure to slice through the compacted surface material, which behaves differently than Earth's soil due to the absence of moisture and weathering processes. The scoop then captured the loosened material before transferring it to a collection container. Chang'e 6 gathered material from multiple spots around the lander, ensuring a more representative sample that accounted for natural variability in lunar soil composition. The arm incorporated sensors to monitor pressure, temperature, and visual data during collection, creating a comprehensive record for scientists analyzing the returned material. With surface collection complete, the mission proceeded to its second sampling phase, subsurface drilling. This critical operation accessed material that has remained protected from space weathering for eons, a scientific treasure locked away since the moon's formation billions of years ago. These shielded subsurface materials preserve information about the moon's original composition without the alterations affecting surface materials. Chang'e 6 deployed a drill system capable of penetrating 2 meters below the lunar surface, deeper than any previous sample collection effort. The hollow spiral bit both cut through the increasingly compacted regolith and transported material to the surface. Operating in stages, the drill periodically retracted to empty collected material into the sample container. The drilling operation overcame significant technical challenges, managing heat without water or air for cooling, maintaining vertical orientation in reduced gravity, and operating with minimal power consumption. Engineers designed the system with automatic safeguards for torque and temperature, allowing the sequence to pause and resume if needed to prevent damage or power system overload. Once both surface and subsurface materials were collected, the samples entered the critical transfer phase to a hermetically sealed container. This operation required extraordinary precision to prevent contamination. The transfer system used enclosed pathways with vibration mechanisms to ensure complete movement of fine-grained materials that might otherwise adhere due to the strong electrostatic forces in the lunar environment. The final sample container represented advanced materials science engineering. Constructed from specialized alloys resistant to extreme conditions, it created a sealed environment with redundant mechanisms to preserve the lunar material in its original state, even through the intense heat of atmospheric reentry. With the samples secured, Chang'e 6 prepared for lunar ascent. The ascent vehicle separated from the lander with perfect timing to rendezvous with the orbiter waiting above. Using a single-stage rocket with non-toxic propellants, the vehicle launched without atmospheric resistance but required precisely calculated thrust for correct orbital insertion. The guidance system used inertial measurements and star tracking to maintain proper trajectory. In orbit, the ascender performed a complex rendezvous with the orbiter circling 200 kilometers above the lunar surface. Both vehicles traveling at 1.7 kilometers per second used radar and optical systems to gradually maneuver closer until achieving physical contact. After successful docking, robotic mechanisms transferred the sealed sample container to the return module. Once the transfer was complete, the ascender separated and was deliberately crashed onto the lunar surface to eliminate orbital debris. The return module, carrying approximately 2 kilograms of lunar material, adjusted its trajectory for the journey home. After the 3-day return trip, the module entered Earth's atmosphere protected by a heat shield designed to withstand temperatures exceeding 2,500 degrees Celsius, landing in China's Inner Mongolia region on July 23, 2023. This intricate process successfully delivered the first ever samples from the lunar far side to Earth, material that has already begun to transform our understanding of lunar history. In laboratories across China, scientists immediately began analyzing these unprecedented samples, uncovering surprising discoveries about the moon's water content, volcanic history, and magnetic evolution. These findings enhance our understanding of lunar development and provide crucial clues about the early history of our entire solar system. The water mystery, a drier far side. One of the most surprising revelations from the Chang'e 6 sample analysis concerns the moon's water content, or more specifically the striking difference in water distribution between the lunar near side and far side. When scientists at the Chinese Academy of Sciences examined 578 individual particles from the returned samples, they discovered something unexpected. The far side contains significantly less water than comparable near side materials. This asymmetry provides crucial insights into the moon's formation and geological evolution that scientists didn't anticipate. The laboratory analysis revealed that far side samples contain only 1 to 1.5 micrograms of water per gram of rock. This measurement represents an extraordinarily small amount, like finding a single raindrop dispersed through an Olympic-sized swimming pool of lunar material. Such tiny quantities required highly specialized detection methods to identify, pushing the boundaries of current analytical techniques. Yet the findings are clear and consistent across multiple samples, confirming a genuine pattern rather than an analytical anomaly. This water content stands in stark contrast to samples previously collected from the near side. Analysis of Apollo mission samples in China's earlier Chang'e 5 mission found water concentrations up to 30 times higher than the far side samples. This disparity represents a fundamental difference in the composition and evolution of the two lunar hemispheres. Detecting water at these minute concentrations requires sophisticated analytical techniques far beyond what was available during the Apollo era. Scientists employed secondary ion mass spectrometry, SIMS, bombarding sample surfaces with focused ion beams and analyzing the ejected ions. This technique can detect elements at parts per billion concentrations, ideal for measuring the lunar water content that exists as sparsely as a few molecules in a vast desert of minerals. Researchers also utilized Fourier-transformed infrared spectroscopy, identifying molecular compounds by measuring infrared radiation absorption. Water and hydroxyl groups create distinctive absorption patterns that scientists can identify even at very low concentrations. By combining multiple analytical methods, researchers gain confidence in their measurements despite the technical challenges. Why would the moon's far side contain less water than the near side? The answer appears connected to the different geological histories of the two hemispheres. The near side experienced extensive volcanic activity between 3.1 and 3.8 billion years ago, creating the dark Maria visible from Earth. These eruptions brought material from deeper within the moon to the surface, potentially including water trapped in the lunar interior during formation. The far side, in contrast, experienced less widespread volcanic activity. Its thicker crust likely prevented magma from reaching the surface in many regions. Without this volcanic transport mechanism, water-bearing materials remained trapped in the lunar interior rather than reaching the surface where Chang'e 6 collected its samples. This explanation connects the water disparity to the broader question of why the two sides of the moon developed so differently. Another factor involves the moon's early history. When the moon first formed, its surface was covered by a global magma ocean that gradually crystallized. During this process, water and other volatile compounds were unevenly distributed, with some regions retaining more than others. The initial distribution patterns may have created a foundation for the water disparity we observe today. Some scientists propose that the water difference relates to the moon's origin through the giant impact hypothesis. This theory suggests the moon formed when a Mars-sized body called Theia collided with early Earth approximately 4.5 billion years ago. During this violent formation process, most volatile, Compounds, including water, were lost to space due to the extreme heat, though some water was retained, potentially in asymmetrical pattern. The water measurements provide important context for understanding meteorite impacts on the lunar surface. When water-bearing meteorites strike the moon, they deliver small amounts of water that can become incorporated into lunar soil. The similar impact rates on both hemispheres should theoretically result in similar water contributions. The observed disparity suggests internal lunar processes play the dominant role in determining water distribution. This finding challenges existing models of lunar water distribution. Previous theories suggested water should be relatively evenly distributed throughout the moon's crust. The Chang'e 6 results indicate we need to revise these models to account for the systematic difference between near and far sides. Scientists are particularly interested in the hydrogen isotope composition of this lunar water. The ratio of deuterium to regular hydrogen provides clues about the water's origin. Preliminary analysis shows isotopic signatures consistent with indigenous lunar water rather than water implanted by the solar wind or meteorite impact, suggesting the difference stems from the moon's formation and internal evolution. The discovery has implications beyond the moon itself. Many rocky bodies in our solar system likely experience similar processes of volatile distribution. The lunar water disparity provides a case study for understanding how water becomes distributed throughout planetary bodies during formation and subsequent geological evolution. For future lunar exploration and potential resource utilization, this finding has practical implications. Missions targeting water resources for potential human settlement should focus on near-side regions, particularly at the poles where water ice may be concentrated in permanently shadowed craters. This water difference represents one piece of a larger puzzle about lunar asymmetry. Combined with other data about crustal thickness, elemental composition, and magnetic properties, it helps scientists reconstruct the moon's complex history. Each new measurement adds constraints to evolutionary models, gradually leading to a more complete understanding of our nearest celestial neighbor. Volcanoes and magnets rewriting lunar history. For decades, scientists believed they understood the moon's volcanic timeline. The prevailing theory suggested that most volcanic activity occurred between 3.1 and 3.8 billion years ago, primarily on the lunar near side, with minimal activity afterwards as the moon rapidly cooled. The far side, with its thicker crusts and limited visible volcanic features, was thought to have experienced even less volcanic activity. Chang'e 6 samples have dramatically changed this picture, revealing a much longer and more complex history of lunar volcanism than anyone anticipated. Laboratory analysis of the return samples shows conclusive evidence that volcanic activity on the lunar far side continued for at least 1.4 billion years, extending far longer than previous models suggested. Scientists determined this by dating volcanic minerals using radiometric techniques that measure the decay of radioactive isotopes, providing precise age measurements of when the rocks solidified from molten material. The samples contained volcanic basalts with crystallization ages between 3.2 and 1.8 billion years old, demonstrating that the moon remained geologically active for billions of years. Like embers that continue to glow long after a fire seems extinguished, the moon's volcanic activity persisted far beyond what scientists believed possible. Rather than quickly cooling and becoming geologically dead after its formation, the moon maintained enough internal heat to drive volcanic eruptions across a span of time that would humble human civilization. This extended volcanic timeline challenges fundamental assumptions about lunar thermal evolution. Traditional models suggested that the moon, being much smaller than Earth, would have cooled relatively quickly after formation. Without the heat-generating processes that keep Earth's interior hot, the moon was expected to have solidified completely within its first billion years. The Chang'e 6 samples prove this assumption was incorrect. The moon retained enough internal heat to continue melting its mantle and producing volcanic eruptions for at least 3 billion years after formation. Scientists are now revising thermal models to explain this prolonged activity. Higher concentrations of heat-producing radioactive elements like uranium, thorium, and potassium than previously estimated may have generated sufficient heat through radioactive decay. Alternative explanations include a different composition for the lunar core or more efficient insulation by the lunar crust that prevented rapid heat loss. Even more surprising was the discovery of preserved magnetic signatures within the Chang'e 6 samples. These signatures indicate that approximately 2.8 billion years ago, the moon possessed a significant magnetic field. Iron-bearing minerals aligned with the prevailing magnetic field when they crystallized, preserving a record of that field's strength and direction as the rocks cooled. This magnetic discovery fills a critical gap in our understanding of lunar magnetism. Previous studies of Apollo samples had found evidence of a lunar magnetic field between 4.2 and 3.6 billion years ago, and again around 2.0 to 1.7 billion years ago. The Chang'e 6 samples bridge the magnetic gap between 3.6 and 2.0 billion years, revealing that the lunar magnetic field endured throughout this period like a steadfast guardian watching over the ancient moon. The strength of the magnetic field recorded in the samples measures approximately 5 microteslas, weaker than Earth's current field, but definitely significant. This measurement provides crucial information about the processes occurring in the lunar interior during this time period. A magnetic field of this strength requires a dynamo mechanism, where flowing conductive material generates and maintains the field. For the moon to generate such a field, it must have had a partially liquid core 2.8 billion years ago. This finding has profound implications for our understanding of the moon's internal structure, suggesting it has a core structure more similar to Earth's than previously thought, with a solid inner core surrounded by a liquid outer core. However, generating a dynamo in a body as small as the moon presents theoretical challenges, as smaller bodies typically cool more quickly. Several mechanisms might explain that unexpectedly long-lived lunar dynamo. One possibility involves precession, where the moon's rotation axis wobbles, creating movement in the liquid core. Other theories suggest large asteroid impacts might have temporarily reactivated the dynamo, or that compositional convection, where lighter elements rise through the outer core during inner core crystallization, drove the necessary fluid movements. The combination of extended volcanic activity and a long-lasting magnetic field points to a fundamental revision of lunar evolution models. Rather than a simple cooling body with a limited geological activity, the moon appears to have been dynamically active for billions of years, like a planetary jewel whose inner fire burns slowly but persistently. Its interior remained hot enough to drive both volcanism and a core dynamo far longer than its size would suggest. These discoveries impact our understanding of other planetary bodies. If the moon remained active longer than expected, smaller bodies throughout the solar system might similarly maintain geological and magnetic activity for extended periods, affecting assessments of potential habitability on exoplanets and the geological evolution of other moons and smaller planets. The moon can no longer be viewed as a simple body that formed, briefly experienced volcanic activity, and then quickly cooled. Instead, it was a complex, active world with diverse volcanic processes and a persistent magnetic field that evolved over billions of years, making it more similar to Earth in terms of long-term geological evolution, though obviously on a smaller scale. As scientists continue analyzing the Chang'e 6 samples, they're encountering more unexpected discoveries, including the identification of exotic graphene in lunar soil, opening yet another chapter in our expanding understanding of the moon's complex composition and history. Graphene on the moon, an unexpected discovery. When researchers began examining carbon content in lunar samples, they made a discovery no one anticipated. Graphene, one of the most advanced materials in modern science, exists naturally on the moon. This finding first emerged during analysis of Chang'e 5 samples from the lunar side and has now been confirmed in Chang'e 6 material from the far side, suggesting this remarkable carbon structure might be widespread across the lunar surface. Graphene represents a unique form of carbon where atoms arrange themselves in a single atom-thick hexagonal pattern, creating essentially a two-dimensional material. Laboratory-created graphene has revolutionized material science on Earth with its extraordinary properties, 200 times stronger than steel, more electrically conductive than copper, and nearly transparent. Finding it naturally formed on the moon seemed as improbable as discovering a perfectly formed diamond in beach sand. The lunar surface, with no atmosphere, extreme temperature variations, and constant bombardment by solar radiation, presents conditions dramatically different from those used to create graphene in laboratories. The analysis revealed that the lunar samples contained few-layer graphene, carbon structures consisting of 2 to 7 sheets of graphene stacked together. These flakes measure just nanometers across, making them invisible to the naked eye, but identifiable through sophisticated analytical instruments that confirmed the distinctive carbon bonding pattern characteristic of graphene. What makes this discovery particularly surprising is the moon's general lack of carbon. Lunar rocks typically contain carbon at concentrations below 50 parts per million, hundreds of times lower than typical Earth rocks. The moon's formation process, which likely involved extreme heating during a collision between Earth and another planetary body, would have driven off most volatile elements, including carbon. Additionally, with no atmosphere to protect the surface, any carbon compounds face destruction from ultraviolet radiation and solar wind particles. Scientists have proposed a fascinating formation mechanism to explain this unexpected discovery. The process likely began with volcanic activity during the moon's more geologically active early periods between 3 and 4 billion years ago. Lunar volcanism released carbon-containing gases that eventually settled onto the surface as elemental carbon. This carbon then underwent transformation through a process called catalytic growth. The key to this transformation appears to be iron-rich minerals abundant in lunar soil. These minerals create efficient catalysts for carbon transformation. When solar wind particles, primarily hydrogen ions traveling at extremely high velocities, strike the lunar surface, they create localized heating and energy transfer. This energy, combined with the catalytic effect of iron minerals, enabled carbon atoms to reorganize into the distinctive hexagonal pattern of graphene. Researchers found evidence supporting this mechanism in the close association between the graphene flakes and iron-rich particles in the samples. Electron microscope imaging shows graphene structures frequently attached to or surrounding iron-bearing minerals, suggesting these minerals provided the catalytic surface needed for graphene formation. The process somewhat resembles chemical vapor deposition, a technique used on Earth, but occurring naturally under the unique conditions of the lunar surface. This natural graphene formation process appears to have occurred over billions of years through the cumulative effect of solar wind interaction with carbon deposits. The process continues today, though at extremely slow rates due to the moon's limited carbon content. The discovery has significant implications for our understanding of carbon chemistry beyond Earth. If graphene can form naturally on the moon despite its harsh environment and limited carbon inventory, similar processes might occur on other airless bodies throughout the solar system. This expands our conception of the complex organic chemistry possible in space environments previously considered hostile to such structures. For materials scientists, the lunar graphene provides a unique opportunity to study natural formation processes that might inspire new manufacturing techniques on Earth. Understanding how graphene forms naturally on the moon might lead to more efficient, environmentally friendly production methods. The specific catalytic role of iron minerals observed in lunar samples could inform the development of new catalysts for industrial graphene synthesis. The presence of graphene also complicates scientific interpretation of carbon compounds detected on other planetary bodies. When instruments detect carbon signatures during space missions, scientists must now consider whether some portion represents graphene structures rather than other carbon compounds. For lunar geologists, graphene provides a new tracer for studying historical processes. The distribution and characteristics of graphene flakes in different regions could offer insights into past volcanic activity, solar wind exposure, and other factors that shaped the lunar surface over billions of years. The discovery illustrates the value of returning physical samples from other worlds. Remote sensing instruments orbiting the moon would never have detected these microscopic graphene flakes. Only through returning material to Earth for analysis with sophisticated laboratory equipment could scientists identify this unexpected component of lunar soil. Perhaps most fundamentally, finding graphene on the moon reminds us that the boundary between advanced human-made materials and natural materials isn't as clear as we might assume. What we consider cutting-edge technology, graphene was first isolated in laboratories in 2004, earning its discoverers the 2010 Nobel Prize in Physics, has been forming naturally on the moon for billions of years through different but equally sophisticated processes. As scientists extract more information from these precious samples, the graphene discovery serves as a reminder that the moon's composition and history are far more complex than previously imagined. Each new finding from Chang'e 6 material pushes us to reconsider assumptions about lunar formation and evolution, while simultaneously revealing that nature itself can create what we consider advanced materials. This makes the discovery both scientifically valuable and poetically significant, the moon silently perfecting China's lunar ambitions, the new space race. While Chang'e 6's scientific discoveries have captured the attention of researchers worldwide, the mission represents something much larger than pure scientific inquiry. China's systematic lunar exploration program forms the cornerstone of a comprehensive, long-term strategy to establish the nation as the dominant space power of the 21st century. Each Chang'e mission builds upon previous achievements, following a methodical progression that contrasts sharply with the more sporadic approach of other space programs. China's lunar program resembles a precisely choreographed ascent up a celestial staircase, beginning with orbital missions, advancing to surface exploration, and now achieving complex sample returns. This methodical climb demonstrates remarkable strategic foresight. Rather than making occasional leaps forward followed by periods of inactivity, China steadily advances one capability at a time, ensuring each step is mastered before proceeding to the next challenge. Chang'e 6's achievement in returning samples from the lunar far side establishes China in an exclusive position. Since the Soviet Luna 24 mission in 1976, no nation had successfully returned lunar material until China's recent missions. More significantly, China stands alone in demonstrating the complete suite of capabilities required for comprehensive lunar exploration, communication relay infrastructure, precision landing technology, sample collection systems, and successful return mechanisms. The implications become clearer when examining China's announced timeline for human lunar exploration. The nation plans to land takenauts on the moon by 2030, following NASA's planned Artemis 3 mission slated for 2027. The critical difference lies in execution reliability. While NASA's program has weathered numerous delays and funding uncertainties, China's space initiatives have consistently met their published schedules. This pattern of reliability extends across their entire space program, from lunar missions to space station deployment. Behind the scenes, China is developing crucial infrastructure for crewed lunar missions. Their next-generation spacecraft, Lander, and heavy-lift rockets already in development. The planned Long March 10th rocket will generate 4,000 tons of thrust, with capabilities comparable to NASA's Space Launch System. Chinese takenauts have begun specialized training for lunar operations, focusing on the unique challenges of the lunar environment. China's ambitions extend beyond initial landings to establishing a permanent research base at the lunar South Pole Shackleton crater. This location holds strategic value due to potential water ice deposits in permanently shadowed regions. Control of lunar water resources provides a significant advantage for sustaining long-term operations and supporting deeper space missions. The proposed base would begin with robotic operations before transitioning to human presence, incorporating modular habitats, power generation systems, and resource utilization facilities. The Chang'e program represents one element of a broader space strategy integrating economic, defense, and diplomatic objectives. The government has designated aerospace as a key sector in its Made in China 2025 industrial plan, directing substantial investment toward developing domestic capabilities throughout the space industry supply chain. This approach aims to reduce dependency on foreign technology while positioning Chinese companies in the growing global space market. China has forged international partnerships to support its lunar ambitions. The International Lunar Research Station, ILRS, initiative with Russia directly challenges the NASA-led Artemis Accords. Since 2016, China has signed over 46 space cooperation agreements with 19 countries and multiple international organizations. Chang'e 6 itself carried scientific instruments from France, Italy, and the European Space Agency, demonstrating China's willingness to offer access to its lunar exploration infrastructure in exchange for international legitimacy. This diplomatic strategy serves multiple objectives. By positioning itself as an accessible partner for emerging space nations, China creates alternatives to Western-dominated space programs while building a coalition aligned with its vision for space governance. These partnerships provide China access to foreign expertise that complements its domestic capabilities, accelerating progress towards space leadership. Unlike the Apollo program, which ended after 6 successful landings, Chinese officials have stated their lunar program has no end and represents a permanent national commitment. This consistency attracts both domestic industry investment and international partners seeking stable collaboration opportunities. China has constructed world-class launch facilities, tracking stations, and research centers dedicated to lunar exploration, representing billions invested in supporting decades of future operations. The Chang'e 7 and Chang'e 8 missions, planned for 2026 and 2028, will survey the South Pole region and test key technologies for the future lunar base, including resource utilization and 3D printing using lunar materials. As China establishes a permanent lunar presence, it will influence international norms for space resource utilization, potentially reshape the global space economy, and challenge established space governance systems. What we're witnessing is not merely a series of scientific missions, but the methodical construction of a new cosmic order where China plays a central role. The implications extend beyond scientific discovery to fundamental questions about which nations will shape humanity's future beyond Earth. As the Chang'e program continues its systematic march forward, it lays the groundwork for China to become the defining force in humanity's return to the moon. The strategic dimension beyond science. China's lunar exploration program delivers scientific discoveries that captivate researchers worldwide, but its significance extends far beyond advancing human knowledge. The Chang'e missions serve multiple strategic objectives that strengthen China's position as an emerging superpower. These missions develop technologies, establish international influence, and position China to compete for the economic and military advantages that space leadership confers in the 21st century. Space technology inherently serves dual purposes. The precision guidance systems for lunar landings translate to military targeting capabilities. Communication networks relaying lunar data enhance military intelligence systems. Sensors analyzing lunar soil can be repurposed for missile detection or surveillance. Each advancement in China's civilian space program simultaneously strengthens its military capabilities, like moves on a strategic chessboard where each position serves multiple functions. This connection became explicit in 2015, when China reorganized its military structure to create the Strategic Support Force, which includes the Aerospace Force (SF). This reorganization designated space as an independent warfare domain, placing China alongside the United States as the only nations with dedicated military space forces. The ASF coordinates military space activities, from satellite operations to counter space capabilities designed to deny adversaries access to their space assets during conflicts. The integration between civilian and military programs follows China's military-civil fusion policy. Technologies developed for lunar missions transfer directly to military applications. Lunar navigation algorithms enhance cruise missile guidance systems and autonomous drones. The relay satellite architecture pioneered by Chang'e demonstrates China's ability to maintain communication networks beyond Earth orbit, capability that enhances military systems designed to function in environments where traditional communication links might be compromised. China's lunar program expertise supports its expanding satellite networks closer to home. The country is developing a low Earth orbit satellite internet constellation providing global coverage under Chinese control. Beyond internet access, these satellites enhance global surveillance capabilities without relying on U.S.-controlled systems. Similarly, China's Beidou navigation satellite system achieved global coverage in 2020, offering positioning accuracy comparable to GPS, while including additional features for military applications. The space sector generates technological advances that ripple throughout China's economy. The program has produced over 4,000 innovations transferred to other industries, from spacecraft materials now used in consumer electronics to miniaturized sensors enhancing everything from smartphones to autonomous vehicles. Like seeds planted in fertile soil, each Chang'e mission cultivates advances in artificial intelligence, robotics, and material science that grow into broader industrial capabilities aligned with the government's strategic economic priorities. Beyond developing technology, China actively shapes global standards governing future space activities through strategic positions in international organizations. By influencing decisions about satellite communications, space traffic management, and technical standards for space infrastructure, China creates an operating environment favorable to its interests, setting the rules of the game before most players have even taken their seats. The economic stakes are enormous, with the global space economy projected to grow from $450 billion today to $1.8 trillion by 2035. Early leadership will capture disproportionate benefits. Lunar exploration develops precisely the capabilities needed for commercial lunar activities, transportation, precision landing, resource identification, and material processing. These capabilities will determine which nations control the emerging markets for lunar resources and services. The moon offers unique resources with significant economic potential. Helium-3 could fuel future fusion reactors. Rare earth elements exist in lunar regolith without the environmental impact of terrestrial mining. Near continuous solar energy at certain lunar locations could power energy-intensive manufacturing processes. By establishing early access, China positions itself to control these resources, claiming prime real estate in humanity's expansion beyond Earth. Perhaps most valuable is the prestige that comes with lunar achievements. Chang'e 6's sample return from the lunar far side demonstrates technological capabilities unique to China, enhancing its status as a technological leader. This prestige translates into diplomatic strength and attracts international partnerships. By offering access to its lunar exploration infrastructure, China creates relationships with nations lacking independent space capabilities, extending these partnerships into economic agreements and political alignment on international issues. As China establishes a permanent lunar presence, it will influence norms governing resource utilization. Control of lunar water resources would provide significant leverage over other nations' operations, as water represents an essential resource for any permanent lunar presence. The technological capabilities, international partnerships, and potential resource control developed through China's lunar program collectively represent a fundamental shift in the global space landscape. Chang'e 6 marks a strategic inflection point in this new space race. As humanity enters an era of sustained lunar development, China has positioned itself to play a leading role, moving pieces across this cosmic chessboard with precision and foresight. The implications extend far beyond the moon itself, reshaping global power dynamics both in space and on Earth as nations compete for the high ground of the 21st century. The Chang'e 6 mission marks a pivotal moment in lunar exploration. For the first time, we have physical samples from the moon's far side, revealing surprising differences in water content, extended volcanic activity, and evidence of a long-lasting magnetic field. These findings fundamentally alter our understanding of lunar evolution. China's methodical lunar program demonstrates technological capabilities that position it as a leading space power with implications for military, economic, and diplomatic spheres. The moon has become an extension of human activity, a frontier where nations compete for knowledge and strategic advantage. What discoveries await as we venture further into this new